So, Rajiuddin, now the stage is yours. Please
Okay.
elaborate.
Thank you for introducing me. So let's start. So as you can see, today I'm going to talk about my recent thought about protecting quantum coherence and entanglement in a correlated channel. So we all know that when a quantum system interact with environments, its quantum correlation decays asymptotically with time. So in this part, basically, I will describe how quantum correlated channel protecting this quantum correlation, like quantum coherence and entanglement. So this is the outline of this talk. So first, I will give you some overview about quantum correlation, like quantum coherence, quantum entanglement, and about general multipartite entanglement. Then I will discuss about some quantum channel like amplitude damping channel, depolarizing channel, phase damping channel, and then how the system, I mean, how the Warner state is extended, Warner-like state is affected by this amplitude damping channel, depolarizing channel. It will be discussed. So let's talk about quantum correlations. So we all know that quantum mechanics has a counterintuitive feature which separating it from classical regime, which is the quantum superposition. And this superposition, due to this superposition, there are several non-classical correlations arises like quantum coherence, quantum entanglement, quantum discord. These are all some type of quantum correlation. So first I will talk about quantum coherence. So what is quantum coherence? So quantum coherence refers to the ability of a quantum system to maintain its entanglement and superposition in the form of interaction and effect of thermalization. So, like if a system interacts with environment, its coherence indicates how much time entanglement will remain and how much the decay will be. So, quantum coherence is measured by several terms like Elon norm of coherence, relative entropy of coherence, skew information. These are all the measurement of quantum coherence, and these measures will satisfy some condition like for incoherent state, the coherence value will be 0, and if there is some completely positive trace preserving map, then it will not change any incoherent operation. I mean, incoherent state. That is, if any CPTV map applied on an incoherent state, it will become an incoherent state. These are some properties. I mean, should satisfy this measure. So first measure is the Elon norm of coherence. Elon norm of coherence is basically the off diagonal term, positive value of this off diagonal of a state. C Elon rho equals to summation of rho I j. These are some off diagonal term. And another measure I will be discussing about this is the relative entropy of coherence. So relative entropy of coherence is here you can see from this equation is S rho diagonal minus S rho. S rho is the von Neumann entropy. So we all know about von Neumann entropy. Von Neumann entropy. We know about this mathematical formula. Also, these are all some, I mean, distance-based measure. So here the S rho diagonal means if you have a state like rho, and if you erase all the off diagonal term, then you will get rho diagonal. And if you calculate the von Neumann entropy of that, then this will get S. You will get S rho diagonal. And if you can calculate the von Neumann entropy of this of the state rho, so if you differentiate that, then you will get, I mean, the subtraction of these two, you will get relative entropy of coherence. Now coming to the quantum entanglement. So like quantum coherence, quantum entanglement is also another quantum correlation, and you can say this is the most wonderful, most wonderful discovery of quantum mechanics, and wonderful feature also. So quantum entanglement is a non-local quantum correlation due to which you cannot represent the properties of a individual subsystem separately. I mean, you have to represent the on of subsystem with respect to other. You cannot separate each other. I mean, you cannot separate the properties of each other. So this is like quantum entanglement. You all know this. So quantum entanglement also have some different type of measure like relative entropy of entanglement, concurrence, and negativity. These are also measures of quantum entanglement, and these measure also satisfy some condition. Like if I give a separable state, then the entanglement must be 0, and for inseparable state there are some entanglement. Some entanglement have some positive value, and the entanglement is is if you do some non-unitary operation on a density matrix, then its entanglement will not change, and entanglement is non-increasing under local operation and classical commutation, that is known as LOCC. So entanglement will be invariant under, non-increasing under LOCC. So these are the properties should satisfy for a bona fide quantum entanglement measure. And now I will talking about some entangled entropy. Entangled entropy for pure bipolar state rho AB is entanglement entropy is simply the von Neumann entropy. So we know how to calculate von Neumann entropy. If you have a system like rho AB, then if you take partial trace, then you will get rho A, and after putting into this formula, you will get von Neumann entropy, which is also known as the entanglement entropy. Right. So after, and now I'm coming to the concurrence. This is the most widely used measure of entanglement for bipartite system, and for mostly for a pure state and multipartite system. So if for a pure state, the concurrence is if you do some spin flip operator on a system, then for pure state the concurrence will be the inner positive value of the inner product of that state and the spin flip operated state. And for mixed state, this the formula is given here. The concurrence of a mixed entangled state is maximum value of 0 and lambda, where lambda is defined as a root over lambda 1 minus lambda 2 minus lambda 3 minus lambda. This lambda is the eigenvalue of a density matrix rho tilde. So rho tilde is defined here. Here the sigma y tensor product sigma is the spin flip operator, right? So this is the concurrence. And there is another measure of entanglement, which is negativity. Negativity is mainly based on positive partial trace criteria, and it is the sum of the absolute value of all negative eigenvalue of a partially transposed density matrix with respect to one of its subsystem. So this is negativity. Now I'm coming to the genuine multipartite entanglement. So what is genuine multipartite entanglement? If you have some n-partite system, and if it is not biseparable, that is if you can biseparate it, then entanglement will be 0. So if it is not biseparable, then it is called genuinely multipartite entanglement. So genuinely multipartite entanglement also should satisfy some condition. So if we measure it by zero, then zero must be 0 for biseparable state, and zero should be positive for genuine multipartite entangled state. It should be positive, and the convexity property also should be satisfied by this entanglement measure, genuine multipartite entanglement measure. And like concurrence value under local operation and classical communication, this is it non-increasing under LOCC. So this measure is also non-increasing under LOCC, and previously like concurrence also under local unitary transformation, the entanglement measure is also invariant. So these are the measures should be satisfied by the genuine multipartite entanglement. And Marcus Haber and the others have given a measure of a genuine multipartite entanglement for n-partite pure state, which is written here, which is simply the minimum value of root over 2 1 minus trace rho I. Here rho I is the partial trace. Suppose you have given a tripartite state shared by three party A, B, C, and you have taken all the possible biseparation like A over BC, B over AC, and C over AB, this biseparation, and you have calculated all the reduced density. Then you will get rho A over BC, rho B over AC. These are like so rho I is like that. So if you put here, then the minimum value will give you the genuine multipartite entanglement for a pure state. And for a mixed state, there is no actually there is a no exact equation of genuine multipartite entanglement. You will get some lower bound of that, which I haven't written here, but you will get some lower bound of this genuine multipartite entanglement for mixed state. Now coming to the genuine multipartite concurrence for a X type state. So as I've already told that for mixed state, there is no, there you will get only lower bound, but if the state is X state, then you will get exact equation of genuine multipartite entanglement. So if you can see from this matrix, this is a type of X matrix. Here all the here only the term along diagonal and anti-diagonal survive, and other terms are 0. And it have to be satisfied some condition like a summation of ai plus b equals to 1 to for normalization condition. And Zi must less than equals to b root over ai by h. So these are the conditions to be a X matrix. And if you have a X matrix, whether it is pure or mixed state, you will get the exact value of genuine. You can calculate the exact value of genuine multipartite concurrence, which is given by this equation: CGMC equals to 2 maximum value of 0 and Zi minus omega I, where omega is written here root over ai by j. So in this way, you can calculate the genuine multipartite concurrence of an X type of matrix. And this formula is first given by Eberle and Haber in 2012, and I have utilized this formula to calculate the dynamics of an entanglement and coherence of an X type of matrix, which I have taken extended order like extent. I will show you later. So coming to the next slide, this is about quantum channel. So what is quantum channel? Quantum channel is a trace preserving completely positive linear map, which map a input state rho 0 into another state rho, like this way. Like rho equals to summation of ek rho naught ek dagger. Here ek and ek dagger are cross operator. So cross operator actually the property of the channel is embedded on this cross operator, and you can write this cross operator like this way: ek is equals to pk on dot of k1 and ak. Here P is the probability. You can tell it as a decoherence strength. I will show you later. So these are the possibilities. Now there are two types of quantum channel. One is memoryless channel or uncorrelated channel, and another is correlated channel. So memoryless channel, what is memoryless channel? When the successive application of quantum channel on the qubits has no memory effect or no correlation. That is, the channel is acting independently on the qubit. Then it is called memoryless channel. In that case, we can write this probability function as you have seen, you see from this here. So we can write this joint probability as the product of individual property of this cross operator. So this you can write. But coming to the correlated channel, when there is some correlation between successive application of channel, then this is called correlated channel. I can say some example. Let's say two qubits passing through a channel in a very short interval of time, such that the channel property has not changed in that time. Then there will be some type of correlation, classical correlation in this channel. So this is known as this correlation is known as a correlated. So this channel is correlated channel. And for this correlated channel, the joint probability can be written as this way, where pk2 over k1 is the conditional probability. Here pkn into p over km minus 1 is 1 minus mu into pkn. Here mu is the strength of this correlation. Like if mu is 0, then the channel is uncorrelated. Channel become uncorrelated. And if mu equals to 1, then channel become fully correlated. You can see from here, delta is the pointer delta. Now we have investigated that dynamics of entanglement and coherence of an input state extended in multipartite extended Orner like state. So this is the convex combination or classical combination of identity matrix and n qubit GIZ class state. So you can see from this here, B is the state parameter. So B is the state parameter, and this state is the known as Orner state, n qubit Orner state. And this is the state parameter, and I here is the identity matrix. So if B is equals to 1, then the state become totally pure state, is a multipartite GZ state. And if the state become, if B is 0, then it is totally a maximally mixed state. So now I will discuss about the result, how amplitude damping channel affect the entanglement coherence, and depolarizing channel affect the entanglement and coherence one by one. So first I will talk about amplitude damping channel. So you can say about the amplitude damping channel is a kind of lossy channel. So you can model it as a two-level system. One is 0 level and another is 1 level. And if the atom is on 0 level, then there is no possibility of transition. But if the atom is at 0 on level, then if the atom is 0 level, then there is no possibility of transition. But if the atom is at 1 level, an excited state level, then there may be some possibility of transition. And you can model this by this two cross operator. One is A0 equals this and A1. These two cross operator will characterize amplitude damping channel. and these are for single qubit. So if you want to operate on a multiple qubit, then the resultant cross operator will be the simply the tensor product of this A0 A1 tensor products, and and this one for memoryless channel. And now coming to the cross operator of correlated channels, like you want to form a cross operator of a n qubits, let's say n qubit cross operator of a correlated channel, and that you can write in this way. So you cannot separate it out. So unlike memoryless channel, you cannot retain it separately. This is a kind of non-separable. So this is a kind of global type of operation. Now, so applying all these cross operator in the extended ordinal like state, we have calculated the output density matrix, and we have calculated the Elon norm of coherence and the genuine multipartite concurrence of the density of this density matrix. So we got the Elon norm of coherence like this. For m equals to 0, that's mean it's a memoryless channel or uncorrelated channel. For uncorrelated channel, we can see from this equation that the coherence is varying with depends on number n. If you increase the qubit number, then the coherence will decay rapidly. But for a fully correlated channel, it is independent of the qubit number. That is, it is totally remain constant irrespective of qubit number. And after that Elon, we have calculated the genuine multipartite concurrence in a similar way. So we obtain these equations of genuine multipartite entangle. So from for m equals to 0, you can see this term is a p-dependent term. So here rho I haven't written, but rho is a function of some p and p. So this term is a function of p and p for uncorrelated channel. But you can see for fully correlated channel, the equation is first term is also is independent of n, but the second term is dependent on n. But this is constant. This is independent of p. That independent of p, that equivalent system. So in this equation, I have written the relation between genuine multipartite concurrence and the Elon norm of coherence. You can see from here. So for a memoryless channel, this relation, I mean, not varying linearly, but for a perfectly correlated channel, the genuine multipartite concurrence varying linearly with Elon norm of coherence. So here I have plotted all the graph for 3 qubit state. The first plot is the Elon norm of coherence for different value of mu. So here you can see it is decays for amplitude damping. The coherence is decay asymptotically and becomes 0 for a decoherence value p equals to 1. And as you can also see, for m equals to 0 to m equals to 1, the decay is delayed. For m equals to 1, the delay is maximum. And in this figure B, I have plotted the genuine multipartite entanglement. And you can see from here there is some entanglement sudden death and after 0.2 value of after 0.25 at p value. But the entanglement sudden death is delayed when we have used the correlated channel. This green curve is for perfectly correlated channel, and this red curve is for uncorrelated channel. So you can see clearly the difference that when we have used when we are using the perfectly correlated channel, the entanglement sudden death is delayed. So this is the 3D plot. So the x-axis is along B, the state parameter B, and the y-axis is AP, and this is the contour plot. So this one for memoryless channel, and this one for correlated channel, fully correlated channel. So from these two figure, also it will be also clear that for perfectly correlated channel, the coherence have some higher value. And from last two figure E and F, we have plotted the genuine multipartite entanglement. And this one for uncorrelated channel, this one for perfectly correlated channel. So this is the boundary, and after that the entanglement is 0. So you can see from if you compare this coherence and entanglement, you can see that there are some region where coherence presents. Here you can see the cursor. Here coherence present, but there is no entanglement. So coherence is more basic than entanglement. So these figures are for 3 qubit, and these are the plot for 4 qubit corner type of state. Now I'm coming to the correlated depolarizing channel. So depolarizing channel is also a quantum noisy channel. It can be modeled as like if you have some state row, then depolarizing channel will affect it like such a way that it become the combination of row and some maximally mixed state. So the cross operator for single qubit depolarizing channel can be written as like this: E0, E1, E2. These are the first one is the identity matrix, and others matrix are simply the Pauli operators. So if we want to write this cross operator for n-dimensional system, I mean n qubit system, so you can write it like this way. So these are some independent tensor product of this individual cross operator. But for a perfectly memory channel, you cannot write it you cannot write it as a tensor product. There is some term pk, so which is not like this p1 p2 etc. So these are the perfectly correlated crossover for perfectly correlated channel, depolarizing channel. So, like amplitude damping channel, we have calculated the L norm of coherence for depolarizing channel also. So, we got some interesting result here. Like for mu equals to 0, that means for an uncorrelated channel, we can see that the coherence is dependent on P and both N. That is, if you increase the qubit number, then the decay of the coherence will be more rapid, and you will observe some certain death of coherence at p equals to 3 by 4 value. But the interesting part is for n equals, when n is even and the channel is perfectly correlated, then the coherence is neither dependent on p, neither dependent on n. That is totally saturated. So we will see some freezing behavior of coherence for a even qubit system, but which is not true on odd qubit system. In odd qubit system, you see some decay of coherence. So like coherence, we have also calculated the genuine multipartite concurrence, genuine multipartite concurrence of that state for a depolarizing channel. And again, we have observed here also that for a n equals to 1, that is perfectly correlated channel, and for even qubit system, we have seen entanglement also freezes, and there is no changes. But for memoryless channel, the entanglement decay rapidly with the increase of qubit number and so on. So from this figure, it will be clear. So you can see this red curve indicates the plotting of Elon norm of coherence for depolarizing channel, for memoryless depolarizing channel, and this blue curve indicates the plotting of Elon norm of coherence for perfectly correlated channel. So for perfectly correlated channel, the decay is less. You can see from here, and we can see we observe some sudden burst of entanglement phenomena. Sudden burst of coherence phenomena here after 0.75 the value. So these are the p plot is the genuine multipartite concurrence plot. So you can see from the green curve is for perfectly correlated channel, and the red curve is for memoryless channel. So here also entanglement start and it is delayed when we are using perfectly correlated channel. So these are some contour plot, how the state is, how the entanglement, how the coherence changes with state parameter v and p is depicted here. And these two are entanglement dynamics. So you can see here there is a sudden burst phenomena. You can see there from this plot here. When n equals to 1, we will observe some sudden burst of phenomenon, sudden burst of entanglement phenomena. And also it is also clear that here there is no entanglement, but some coherence is present here. And these all plots are for 3 qubit state, and these plots are for 4 qubit state. Now you can see this is the 4 qubit plot. So first two plot is for coherence, Elon norm of coherence, and the second two plot is genuine multipartite entanglement. So for perfectly correlated channel, that is n equals to 1, you can see the constant value, that is the freezing behavior of Elon norm of coherence. But for uncorrelated channel, there is no freezing behavior we have observed. Similarly, for coherent entanglement also, we have seen the freezing behavior for perfectly correlated channel. So coming to the conclusion, so the conclusion is we have observed the freezing phenomena for quantum coherence and genuine multiple type concurrence for even qubit order-like state in a perfectly correlated channel. But for odd qubit order-like state, we haven't any observed any freezing type of behavior. And this behavior is we have seen only for depolarizing channel and phase damping channel. Although I haven't written the result of phase damping channel for complex shifting. So you can see from the paper. But in case of amplitude damping channel, we haven't seen any we haven't seen any freezing behavior of quantum entanglement, multipartite entanglement, and coherence. We haven't seen any type of things. And another interesting case, we have observed that the sudden breadth of entanglement phenomena order like step in case of correlated depolarizing channel. So thank you. These are the all.
Thank you, Rajiuddin, for a nice presentation and elaboration of the correlated channel.
Yes, thank you.
So, is there any question? Please ask question or doubts. Please ask Rajiuddin. Any questions or doubts? Okay, so if there is no questions, thanks Rajiuddin once again.
Can I?
Okay, so our next speaker is Karthick Selvan, who is from Department of Physics, Thiagarajar College from Madurai. I request Karthick, please share your talk.
So, am I audible, sir?
Yeah, you are audible and your screen is visible.
Okay, thank you, sir. So, good morning to all. So, before I start my presentation, I would like to thank Professor Prashanta K. Panigrahi and other organizers of QIQT 2022 for giving me this opportunity. So, the topic I'm going to present today is multi-photon coherence effects in multi-level atomic systems. So, the objective is to discuss about my paper, where I have studied the multi-photon coherence effects on the absorption and dispersion of two weak probe beams in double inverted Y system using density matrix formalism. I will start from the basics. First, I will describe the absorption and the dispersion phenomena in two-level atomic system, and then I will show how the multi-photon coherences modify the absorption and dispersion of a weak probe beam in 3-level, 4-level, and 5-level atomic systems. And then I will present my paper, and in the last slide I will give the conclusion of this presentation. Okay, so first I'll start from the two-level atomic system. So here I have considered two levels of an atom. So the ground state is labeled as ket1 vector, and the excited state is labeled as ket2 vector. And these two states are coupled by probe beam, weak probe beam. And here I'm going to follow semi-classical approach, where the atom is treated quantum mechanically and the electromagnetic fields are treated classically. And this is the density operator of the atomic system. So here rho 11 and rho 22 are the populations, and rho 12, rho 21 are coherences. And this is the atomic Hamiltonian. So in this Hamiltonian, E1 is the energy of the ground state, and E2 is the energy of the excited state. And the atom field interaction Hamiltonian is given here. So in this expression, this mu hat is the dipole operator, and E vector is the electric field vector, and small omega p1 is the angular frequency of the probe beam. So this expression can be expressed as given here. So in this expression, this capital omega P1 is the Rabi frequency of the probe beam, and it is defined as mu21 vector dot E vector divided by H cross. Here mu21 vector is the element of the dipole operator. So here I have rewritten the interaction part of the Hamiltonian in the interaction picture, and this is given here. So this term, this Hamiltonian has two exponential terms, and the argument of these two exponential terms are different. And since we are going to consider only the resonant process, we can ignore the second exponential term, which is rotating fastly. So this is called a rotating wave approximation. So after making rotating wave approximation, the Hamiltonian can be reduced in the form given within this box. So here this delta P1 is the detuning of the probe beam. The equation of motion of the two-level atomic system is given here. So this is the Heisenberg equation of motion. In addition, we have to consider the decay processes occurring in the atomic system, because once we excite the atom from the ground state to excited state, it is not going to stay there forever. It will decay to the ground state by a spontaneous emission process. So we have to consider the decay processes also. So in this expression, if we substitute for the Hamiltonian and the density operator, we will have the terms with this exponential factor. So this exponential has time t, but here our objective is to find the steady state solution of the coherence term as a function of probe beam detuning. So in order to get rid of this time dependent factor, I have defined new density operator elements. So here the rho prime 21 is defined as rho prime 21 into exponential of I delta P1 t. So for this new coherence term, the equation of motion can be written as given here. So here the small gamma 21 is equal to capital gamma 2 by 2 minus I delta P1, and here the capital gamma 2 is the decay rate of the excited state 2. And under weak probe beam approximation, we take the population of the ground state as 1 and the population of the excited state as 0. And in this approximation, the steady state solution of the coherence term can be written as given within this box. So this equation can be obtained from this equation, differential equation, by taking the left hand side as 0 and in the right hand side substituting 1 for rho prime 11 and 0 for rho prime 22. And now, why we are interested only in this coherence term? Because this coherence term is related with the optical susceptibility of the medium, and the relation is given here. The optical susceptibility is a complex quantity, so it has real and imaginary part, and this real part is proportional to real part of rho prime 21, the coherence term, and it describes the dispersion of probe beam, and the imaginary part is proportional to the imaginary part of atomic coherence, and it describes the absorption of probe beam. And the group index, it depends on the slope of the real part of rho prime 21, and if the slope is positive, it indicates that the group velocity is smaller than the speed of light in vacuum, and in that case we have subluminal propagation of light. If the slope is negative, then it indicates that the group velocity is larger than the speed of light. In that case, we will have the superluminal propagation of light. So here I have plotted the real and imaginary parts of the atomic coherence. See, the blue curve is the imaginary part and the red curve is the real part. So here we can see that when the delta P1 becomes 0, the detuning becomes 0, we have the resonant absorption of probe beam. And within this resonant region, we have the anomalous dispersion of probe beam. So now I consider a 3-level atomic system. So here the level 1 and the level 2 are coupled by a weak probe beam with Rabi frequency omega P1, and level 3 and the level 2 are coupled by a strong control beam with Rabi frequency omega C1. So this control beam coupling is assumed to be resonant coupling. And in this level scheme, we have two coherences. One coherence is between the level 1 and the level 2. It's a 1-photon coherence. And another coherence is between level 1 and 3. But the transition between level 1 and 3 is dipole forbidden. So these two levels are coupled by both the probe beam and control beam. So it is called 2-photon coherence. Now the Hamiltonian in the interaction picture with rotating wave approximation can be written as given here. So it will have two terms corresponding to this two transition and their Hermitian conjugates. And we have to write the equation of motion for both one photon coherence and three photon coherence. And this is the equation of motion for the coherence terms. And again, I have redefined the density operator elements in order to get rid of the time dependent factor. Now, again, under weak probing approximation, we take rho prime 1 is equal to 1 and rho prime 2 is equal to 0 and keep the terms which are only first order in omega p1. Then under this approximation, the steady state solution of the coherence term rho prime 2 can be written as given here. So if we compare this solution with the solution in the two-level atomic system, this one, you can see that we have an additional factor 1 plus f in the denominator, and the expression of f is given here. So if one tries to solve this set of coupled differential equation to find the steady state solution, we can realize that this factor 1 plus f is due to the presence of this two photon coherence term rho prime 3 1. So here we have the effect of the two photon coherence in both absorption and dispersion of probing. So here I have plotted the real and imaginary part of the atomic coherence. So here we can see that when delta P1 becomes 0, instead of a resonant absorption, we have sharp decrease in the absorption, and it is called electromagnetically induced transparency. This electromagnetically induced transparency will occur when two photon resonance condition is satisfied. So the two photon resonance condition means the frequency difference between these two lasers should be equal to the frequency corresponding to the energy difference between these two levels. And here I have considered the control beam coupling is resonant coupling. So when this delta P1 becomes 0, the two photon resonance condition will be satisfied. So and we will have electromagnetically induced transparency. So this is what has occurred here, and within this transparency window we can see that the slope of the dispersion curve is very steep and it is positive, so we can have slow light in this case. Next, I consider 4-level atomic system. So here the level 1 is coupled to level 2 by a weak probe beam with Rabi frequency omega p1, and level 3 is coupled to level 2 and the level 4 by two control beams with Rabi frequencies omega c1 and omega c2 respectively. Here we are interested in three atomic coherences. One is a one photon coherence between the level 1 and 2, and another one is a coherence between the level 1 and 3. This is a two photon coherence, and third one is the coherence between the level 1 and 4. It is a three photon coherence because this level 1 is coupled to level 4 by three laser beams. And again, the Hamiltonian of the system can be written as here. So here we will have three terms corresponding to these three transitions and their Hermitian conjugates. And the equation of motion is written for three coherence terms. And again, under weak probe approximation, the steady state solution of the atomic coherence can be written as given here. So if we compare this with the case of three-level atomic system, we have the term 1 plus f prime in the denominator of f. And the expression of f is given here. This is the same as in the case of a three-level atomic system, but the expression of f prime is given here. And again, we can verify that this term 1 plus f prime arises because of the presence of three photon coherence, this rho prime 4 1 in the equation of motion. So now we will see the effect of this 1 plus f prime term in the absorption and dispersion of a probe beam. So here I have plotted the real and imaginary parts of the coherence term, and when delta P1 is equal to 0, the absorption is decreased, but it's not decreased very much. So now I consider the 5-level atomic system, and here the level 1 is coupled to level 2 by a weak probe beam with Rabi frequency omega p1, and level 3 is coupled to level 2 and 4 by two control beams with Rabi frequencies omega c1 and omega c2 respectively, and level 4 is coupled to level 5 by third control beam with Rabi frequency omega c3, and all these control beam couplings are resonant couplings. So here we will have four coherence terms. One is a single photon coherence between the level 1 and 2, and another one is a two photon coherence between level 1 and 3, and the three photon coherence between level 1 and 4, and the four photon coherence between the level 1 and 5. And in the Hamiltonian of the system, so I have not written the Hamiltonian and the equations of motion for the system, because we can easily extend the Hamiltonian and the equation of motion of four-level system to this five-level atomic system. So in the Hamiltonian, we will have four terms corresponding to this four transitions and their Hermitian conjugates, and we will have equation of motion for all these four coherence terms. So I have directly given the steady state solution of the rho prime 2 1, and it is this expression is given here. So as compared to the four-level atomic system, we have the term 1 plus f double prime, the denominator of f prime, and the expressions of f and f prime are same as in the case of four-level atomic system. So, and this f double prime, this arises because of the this four photon coherence. Here I have plotted the real and imaginary reports of the atomic coherence. So when the detuning becomes 0, the absorption is decreased, but it is not decreased to 0. However, the reduction in the absorption is more as compared to the four-level atomic system. So here I have compared the absorption and dispersion of weak probing for all four systems. Say in the two-level system, we have resonant absorption of a probing, and within this resonant region and the anomalous dispersion of probing. And in three-level atomic system, so when the two-photon resonance condition is satisfied, we have electromagnetically induced transparency. That is, the absorption is reduced sharply when the two-photon resonance condition is satisfied, and this is decreased because of the presence of the two-photon coherence term. And in the four-level system, we can see the transmission is decreased. So we can say that in the four-level system, the transmission induced by the two-photon coherence is decreased by the presence of three-photon coherence in the four-level atomic system. And in the five-level atomic system, we can see the transparency is more as compared to the four-level atomic system. So here we can say that the absorption induced by the three-photon coherence in the four-level atomic system is decreased due to the four-photon coherence present in the five-level atomic system. So from this, we can say that the atomic coherences created by odd number of photons induce absorption, and the atomic coherences created by even number of photons, they induce transparency. So now I will describe my paper. So in my paper, I have considered the five-level double inverted Y system, and the level scheme is given here. Instead of one probing transition, I have considered two probe transitions, and this level 0 is coupled to level 2 and 3 by two probings with Rabi frequencies omega p1 and omega p2 respectively, and the level 1 is coupled to level 2 and 3 by two control beams with Rabi frequencies omega c1 and omega c2 respectively, and this level 3 and 2 are coupled to level 4 by two more control beams with Rabi frequency omega c4 and omega c3 respectively. So in the system, we have two photon coherence between the level 0 and 1. So this coherence can be created via two channels. The one is from 0 to 2 and 2 to 1, and another one is from 0 to 3 and 3 to 1. So we have two routes to create this two photon coherence, and we have another two photon coherence between the level 0 and 4, and this can also be created via two routes. One is from 0 to 2 and 2 to 4, and another one is from 0 to 3 and 3 to 4. And for the probing transition between the levels 0 and 2, the coherence between the level 0 and 3 is the three-photon coherence, and this can also be created via two channels. One is from 0 to 2, 2 to 1 and 1 to 3, or 0 to 2, 2 to 4 and 4 to 3. Similarly, for the transition between the levels 0 and 3, the coherence between the level 0 and 2 is a three-photon coherence, and it can be created, or it can also be created by two channels. One is from 0 to 3, 3 to 1 and 1 to 2, and another one is from 0 to 3, 3 to 4 and 4 to 2. So in the system, we have two photon coherences and two three-photon coherences, and each of them can be created via two channels. So here I have written the Hamiltonian of the system in the interaction picture with rotating wave approximation, and the equations of motion for the coherence terms are written here. And under weak probing approximation, the steady state solutions of rho prime 20 and rho prime 30 are written here. If we see here, we have two terms in both coherence terms, in both coherences. The first term is similar to the case of single probing transitions we saw earlier. So, for example, in the rho prime 20, the first term is I omega p1 divided by 2 into gamma 20 into 1 plus G prime divided by 1 plus G double prime. So this describes the absorption and dispersion of first probe beam, and the effect of the terms G prime and G double prime, they exist because of the existence of 2 photon and 3 photon coherences. And if you look at the second term, we have this radio frequency omega p2. So it comes from the other probing transition. And this second term, it describes a 3 photon process. See, for example, this first term can be explained as absorption of the first probe beam and the emission, second probe beam for radio frequency omega p2, and the emission of a control beam with radio frequency omega c2, and the absorption of a control beam with radio frequency omega c1. So this 3 photon process occurs via lambda channel. So this channel, absorption of omega p2 and the emission of omega c2 and absorption of omega c1. Similarly, this term also can be explained, and we can verify that this 3 photon process, it occurs via the ladder channel. So in a similar way, we can explain the terms in the expression of rho prime 30. So in the atomic coherences, rho prime 20 and rho prime 30, we have 2 contributions. One is from QI1 process. That one is the first term. I have denoted this term as rho prime 120, and the second one is due to QI3 processes, the 3 photon processes. I have denoted this as rho prime 320. In the same way, I have written this rho prime 30 also. So in this expression, we have G prime, G double prime K, and here H prime, H double prime K. So the expression of K is given here. And the G prime, G double prime, H prime, and H double prime are given here. So if you look at the expression of K, G prime and H prime, see the last terms of these terms of this G prime, H prime, and K are same. And this last term appears due to the closed loop structure formed by the 4 control beam transitions. And in the paper, I have referred this term as interference term because we can change the values of this term by changing the relative phase difference between the control beams. So here this rho prime 120 and rho prime 130, they describe QI1 processes for probing omega p1 and omega p2 respectively. So in the absence of interference term, G prime is equal to H double prime. So if you see here, this is the expression of G prime, this is the expression of H double prime. So the G prime describes the effect of 2 photon coherence for the probing 1, and the H double prime, it describes the effect of 3 photon coherence for the probing 2. So when this interference term is not present, we can see that G prime is equal to H double prime. And similarly, the H prime will be equal to G double prime. So H prime, it describes the effect of 2 photon coherence for the probing 2, and G double prime, it describes the effect of 3 photon coherence for probing 1. And when this term is not here, these 2 terms, this H prime and G double prime are same. So from this, we can say that if you increase the radio frequencies omega c2 and omega c4, they enhances the effect of 3 photon coherence for probing 1 and the 2 photon coherence for probing 2. Similarly, if you increase the radio frequencies omega c1 and omega c3, they provide the transmission for the probing 1, the transmission, increase in transmission for the probing 1, this, which is the effect of 2 photon coherence, and increase in the absorption of probing omega p2, which is the effect of 3 photon coherence. So in the presence of the interference term, the effects of 2 photon coherence are enhanced for both probings because this interference term, it it is present only in the expression of G prime and H prime, and they describe the effect of two photon coherence for the probing 1 and probing 2. And these terms rho prime 320 and rho prime 330, they describe Chi3 processes occurring via lambda and ladder channels, and the imaginary part of these terms, they describe the gain. So the both Chi3 processes and the effect of interference term depend on the relative phase difference between control beams. And the steady state solution, I have rewritten the steady state solutions here. Actually, these solutions I have rewritten here. So this is the form I have given in my paper, and the interference term, it will become 0 when the omega C1 divided by omega C2 is equal to omega C3 star divided by omega C4 star. So it can be verified from the expression of this interference term. When omega C1 by omega C2 is equal to omega C3 star by omega C4 star, the numerator will become 0. So there will be no the interference term. And similarly, when the ratio of Rabi frequencies of control beams forming the lambda channel, so the first two control beams, they form lambda channel. So we can see this in the level diagram. So these two control beams, they form the lambda channel with the two probe beams. When this ratio and the ratio of Rabi frequencies of two probe beams forming ladder channel and the ratio of Rabi frequencies of two probe beams are equal, we will have only the effect of two photon coherences. That is, when this condition is satisfied. So in this expression, in the expression of rho prime 20, this term will be cancelled by this term, and this term will be cancelled by this term, and we will have only the first term alone. So this is merely the absorption and dispersion of a weak probe beam, and the k, the parameter, the factor k in the denominator, it describes the effect of two photon coherences. Similarly, when this condition is satisfied, in the second, the expression of rho prime 30, this term will be cancelled by this term, and this term will be cancelled by this term, and we will have only the first term alone, which describes the absorption and the dispersion of weak probing and the effect of two photon coherences on it. And when omega C1 by omega C2 is equal to omega P1 by omega P2, we will have three photon coherence effects occurring only via ladder channels, meaning when this condition is satisfied, only this term will be cancelled by this first term in the rho prime 320, and the third term will not be cancelled. So we will have the three photon coherence effects only via ladder channels. So the terms within this square bracket, they describe the effect of three photon coherences. Similarly, when omega C3 star by omega C4 star is equal to omega P1 by omega P2, we will have the three photon coherence effects occurring only via lambda channel. So in this case, the last term will be cancelled by the last term in rho prime 320. Similarly, in rho prime 30, the last term here, it will be cancelled by this last term, and we will have the three photon coherence effects occurring via only the lambda channels. And finally, when phi 12 is equal to phi 3 is equal to pi, here phi 12 is the relative phase difference between the control beams forming lambda channel, and phi 34 is the relative phase difference between control beams forming ladder channels. So when they are equal to pi, both probe beams undergo absorption, and this phenomena is referred as correlated two-signal absorption in double lambda system. So the same phenomena occurs when this condition is satisfied in double inverted Y system also. Here I have shown that this is due to the contribution from Chi3 processes. So these are the plots, and this all these points can be verified from these graphs. So in this graph, the first row, it is absorption of probing 1 and 2. So here the solid line is for probing 1 and the circle line is for probing 2. And in the second row, I have plotted the gain for the probing 1 and 2 for three different cases. And in the third row, I have plotted the net absorption for both probe beams, and in the fourth row I have plotted the net dispersion for both probe beams. So in all these three cases, the interference term is taken, the Rabi frequencies of control beams are chosen such that the interference term is 0. And in the third case, omega C2 and omega C4 are increased 3 times as compared to omega C1 and omega C3. So in the net absorption profile, if you look at, we have net absorption for the probe beam 1 and a net gain for probe beam 2. So in this graph, I think this 0 line is very, it's not, I think it is visible. So the absorption curve of probe beam 2 has gone below the 0 line. So it indicates we have a gain for the probe beam 2 and the absorption for probe beam 1. So in this case, if you look at the slope of the dispersion curve, for the probe beam 1, the slope is negative, and for probe beam 2, the slope is positive. So here, one beam can travel with a larger group velocity, and another beam can travel with a small group velocity. So for these graphs, the interference term is not 0. So the Rabi frequencies are chosen such that the interference term is not 0. So if you compare these plots with these plots, see, we will see the absorption is decreased for both probe beams in all three cases, and the gain is also decreased when the resonance condition is satisfied for all probe beams. It is because of the presence of the interference term, and this is the net absorption and the net dispersion of probe beams to both probe beams. See, in the last case, if we see, the absorption of both probe beam is nearly 0. So you can see this point. And if you look at the dispersion curve, and the dispersion curve is negative for the probe beam 1 and positive for probe beam 2. So here we have both subluminal, we can have both subluminal and superluminal propagations with nearly 0 absorption of both probe beams. So the system is more suitable for producing slow fast light pairs. So here I have plotted the absorption gain and the net absorption and net dispersion for different the relative phase difference between control beams. So in this graph, mainly I just want to point out the third curve in the third column. So this corresponds to 512 is equal to pi and 543 is equal to pi. So in this case, if you look at the only the Chi1 process, so we have the reduction in the absorption for both probe beams. But if you include the Chi3 contribution in the net absorption profile, both probe beams have undergone resonant absorption. So this is this process was referred as correlated true signal absorption in another paper in double lambda system. Here also we have the same process, and here I have shown it. We can verify that this resonant absorption is coming from is due to the contribution of Chi3 processes. Okay, so the conclusion. So the generation of atomic coherences, they modify the absorption and dispersion of a weak probe beam. So we saw that the coherences created by odd number of photons, they induce absorption, and the coherences created by even number of coherences, they induce transmission. In 5-level double inverted Y system, the two probe beam transitions are also affected by phase-dependent Chi3 processes in addition to the atomic coherence processes. And the closed-loop structure formed by 4 control beam transitions, they enhance the effect of 2 photon coherences. And by changing the ratio of the Rabi frequencies and the relative phase difference between the control beams, the linear response of the medium to probe beams can be modified. And it is possible to have X-type absorption spectrum. So here the X-type means the slope of the dispersion curve for one probe beam is positive, and the slope of the dispersion curve for another probe beam will be negative. So we will have this shape of AX. So we can have the X-type absorption spectrum with reduced absorption of both probe beams. So in this case, the absorption of both probe beams is nearly 0, but we have this X-type of dispersion. So the system is most suitable to produce slow fast light pairs. So these are the references. So I presented the results from these papers, and the last one is my paper. So thank you. So if you have any question, I'll try to answer the questions.
Thank you for your nice presentation. So if there are any doubts or questions, please, you can ask. Okay, I have a couple of questions.
Yes, sir.
Can you please go back to your either fourth or fifth level figure? Yeah, just that basic one. Yeah, that one was fine. So
okay,
here, I think you have not
yes, sir.
mentioned.
I will show this. This one, 5-level atomic system.
That's fine. I think you have not mentioned it, but you probably assume that state 2 and 4 they are forbidden.
Yes, sir.
Okay,
Yes,
because
actually we can choose this 5 levels. For example, the level 1 and 2, it can be chosen as the ground state hyperfine levels of rubidium 87 or some alkali atoms, and similarly this level 2 and 4 we can choose them as a hyperfine levels in the either p 3 by 2 fine structure manifold or p half fine structure manifold, and similarly this level 5 we can choose it as one of the hyperfine level in the d 5 by 2 fine structure.
Okay, and can you go to your slide that represents the states of your inverted double Y structure?
Yes.
Yeah. So here it's basically a combination of two EIT system, right?
Yes, sir. Yes, sir.
Yeah. So when you mention about that your dispersion is positive, negative, based on that you can comment on subluminal or superluminal. How do you comment? I mean, on what basis you comment that it is subluminal or superluminal?
Because the slope is negative, slope of the dispersion curve is negative for one probe beam, and the slope of the dispersion curve is positive for another probe beam. Because one beam undergoes absorption and another beam undergoes a transmission. So the slope will be opposite. So we can have the group velocity, large group velocity for one probe beam and a small group velocity for another probe beam.
Okay. Yeah. Thank you very much.
Thank you, sir.
So if is there any other question? Okay, so if not, let's thank the speaker for his excellent presentation. Thank you, Karthik, once again.
Thank you, sir. Thank you, sir. Thank you very much.
Okay. So our next speaker is Varun Srivastava from ICCR Kolkata. So, Varun, please share your presentation file. Yeah, just full screen it. Okay. So Varun is going to talk about exact time evolution of genuine multipartite correlation for n-cubic systems in a common thermal reservoir. So Varun, please carry on.
Background disturbance.
Yeah, Varun, your background noises is too much.
Yeah, is it from my side? Yeah, now it's fine. Now it's fine. Yeah, so
yeah, now it's fine. Please
hello
carry on.
everyone. Today I will be presenting a work that we did in this lab last year, in which we studied the dynamics of correlations of multipartite system in a common thermal reservoir. So this was the work, and so the motivation behind this work was twofold. First of all, it involves the study of multipartite correlations. So, and we know that multipartite entanglement plays an important role. It's a very it's a significant resource. For example, it has been shown that 3-qubit maximally entangled GSZ states show much greater non-locality than Bell states, and for teleportation protocols, multipartite systems have been shown to be more robust. So therefore, it is of interest to study dynamics of genuine multipartite correlations. And here, so I'll as I move along, I'll explain for what correlation measures we use for studying these. But the second motivation behind using this work, doing this work, was that in realistic scenarios, a quantum system is never isolated. It's always coupled with its environment. So we try to model that. And when a quantum system is coupled with the environment, it shows an decoherence due to environment. And we try to show that in a multipartite scenario. So the overview of the work is, as I said, we studied this multipartite n-qubit correlated states. And these are coupled with a common thermal reservoir. To model the reservoir, we used a set of infinite harmonic oscillators, and which were at some temperature T, corresponding to the temperature of the reservoir. And the interaction between the qubits and the reservoir that we used was a non-trivial bilinear form, and so we used an interaction Hamiltonian that commuted with the Hamiltonian of the n-qubit system, so that our system was non-dissipative. So we obtained an interesting result, which as we move along, I'll illustrate. But the result was that for certain states, we found that we could have robustness against the environmental decoherence. So as we move along, I will make this point clear. So yeah, first of all, I would like to discuss the model that we use. So our total Hamiltonian, the total Hamiltonian of the n-qubit system and the reservoir was given by this. This HS term, which is the system Hamiltonian of the n-qubit system, is given by this expression, where this omega I, so the energy gap between the qubits is 2 omega. So the Hamiltonian for the n-qubit system is given by this. And the reservoir, as I said, was modeled by a set of infinite oscillators, where this A dagger are the familiar annihilation and creation operators, that boson annihilation and creation operators. And as I said earlier, the interaction Hamiltonian was a simple bilinear Hamiltonian that we used, which was given by this term. So using this, so if we go back, we have used this extra term, this is the renormalization term, which helped us to perform a unitary transformation. And after performing this unitary transformation on the Hamiltonian decouples into the n-qubit part and the reservoir part. Using this, it is easy to calculate the evolution of the density matrix of the system, which so our starting point was to initially consider that the n-qubit system and the reservoir are in a product state. So there is no correlation between them. And the reservoir, the density matrix of the reservoir, the initial density matrix was given by this term. where this beta represents the inverse temperature. So our reservoir would be at some temperature T, and this beta represents the inverse temperature. But our motive was to calculate, study the dynamics. We want to study the dynamics of the n-qubit system. So for that, we would have to trace out the reservoir part from the total density matrix. And so our initial states for the n-qubit system were taken over of the form of this form, and so it is easily seen that this state is an eigenstate of the Hamiltonian Hs over here. So the next step was to find the expression for matrix elements to see the time evolution of the off-diagonal elements. Why are we interested in the evolution of off-diagonal elements? Because their evolution would tell us how the coherence of the system is affected as as time moves along. So typically we expect that as the system evolves through time, the off-diagonal elements should vanish, and so there is less coherence in the system. So for calculating the matrix elements, we have this term which would be important later on, this Q2 term, which as I move along, I'll show how we use this. But an important term over here is also this j omega, which is the spectral density, which we had to put in a ad hoc manner. So we studied different systems for different spectral densities. For an explicit example, we first considered the dynamics of genuine multipartite correlations in a GSZ class Werner state. So, which is given by this expression here. This psi represents some pure entangled GSZ type state, and this X here is between 0 and 1, and it is called the mixing parameter. For such a state, we calculated the concurrence, which is given by this expression, and we are interested in calculating the dynamics of this term. So this is an explicit form of state that we started from. For this, the concurrence is given by this expression. So take a look at this expression. We can see that this Q2 term appears over here, and Q2 is typically a positive and increasing function. So and it increases with time and temperature. So as we can see over here, as Q2 will increase, the correlation, this concurrence would decrease, and after some time we expect that this would go down to 0. So yeah, so to study this in more detail, we took an explicit form of spectral density. This is a very simple form of spectral density, which for 0 temperature gives the value of Q2 to be this. And putting this in the previous expressions, we we plotted the concurrence, how the concurrence would evolve with time. So there is something called a preservation time, which is the amount of time for which the correlation remains in the system, after which the system experiences certain depth of correlations. So for x, for any value that is not equal to 1 for x, we have some finite amount of time for which the system retains some correlations, and we plotted the concurrence dynamics for various values of mixing parameters and for various values of the interaction strength given over here in the term for the spectral density. An interesting result was obtained when we took the initial state psi to be of this form, an antisymmetric form. When we use this, the off diagonal terms, the expression for the off diagonal terms came out to be this. And as you can see that it is very clear from this expression that if we take this approximation, that all the frequencies, all the energy gaps between the first qubit till the n-1 qubit, if those are taken to be approximately equal to the nth qubit, then we can see over here that this the off diagonal term would be approximately constant. So our the off diagonal terms physically represent the coherence of the system, and if those are not decaying, then we can say that the system is showing robustness against environmental decoherence. Sorry. And a physical reason for this is that if under this approximation, our initial density matrix is close to an equilibrium state, which means that our density matrix is commuting with the total Hamiltonian of the system. And if that is the case, then the system would show robustness. Another system that we considered to studying the dynamics of was the W class Werner state. And for simplicity, we took the n equal to 3 case scenario over here. Again, the same procedure was applied and we calculated the off diagonal terms. And again, we observed that if the frequencies, all the frequencies are taken to be equal. So this is a different kind of constraint. But if this omega A, omega B and omega C are taken to be equal, then off diagonal terms again would not decay. And our system in this case would again show robustness against environmental decoherence. So for the W class Werner state, we measured the decoherence, which is quantified by the von Neumann entropy. And depending on mixing parameter, the decoherence saturates at some time, which is shown by this graph. For different mixing parameters, we saw that this decoherence will saturate at some particular time. We also saw that if for a particular mixing parameter, in this graph, we took the mixing parameter to be 0.9. As we increase the this value of eta, the rate at which this decoherence saturates also increases. So in conclusion, we studied different the dynamics of the genuine multipartite correlations for different states, particularly GSZ and W type states. And for different spectral density, I only showed the one example of a very simple form of spectral density that we took, but we did this for some other spectral form of spectral densities also. And we saw that the system encounters the sudden death of entanglement after some time. And an extension to this work could be that we study qubits placed in different separate environments, and through that we could study the various type of thermodynamical aspects and for such a system. That would be for some future work. So thank you.
So thank you for your nice presentation. So if there is any questions or doubts from the audience, please ask. Okay, but I have one short question.
Yeah.
So in your model, you have assumed that summation over I, that is goes from 1 to n is equal to no a few slides later, where you assume summation over omega I is equal to omega n.
Oh, yeah.
Yeah.
In this one.
Right. So in that case, your density is going to be a constant.
The off diagonal elements, the evolution over time doesn't change the off diagonal elements.
Right. So are we losing any generality by assuming through this assumption? If we don't assume that,
then of course the off diagonal elements would decay with time. But we saw that for this particular case, where the summation over all the omega i's except the nth one is equal to the energy gap between the nth qubits. For this particular case, the off diagonal elements won't decay. It would be approximately a constant. So this kind of state would be used to model scenarios where the system shows robustness against decoherence, and if it's kept in a some thermal thermal environment or something like that. And the thing is, such states, this can be obtained, for example, in NMR. For a two-party state, we have technology to like tune the energy gap between the qubits. So this might have actual physical applications. So yeah.
okay. So Professor Panigrahi probably has questions. Sir, please.
Yeah, I have a small question.
Yes.
See this, referring to again this slide. So are you implying that it is like a synchronization? You know, for example, all the omega is summing up to 1 omega m, and you know, this reminds me of some kind of synchronization or something like a quantum Darwinism when one state is stable. Does it imply something like that?
So I would have to think about that. I haven't thought about this synchronization. I would have to think about that. I'll look into it.
Yeah, sure. Thanks.
Is there any other questions from the audience? Okay, if not, then let us thank the speaker once again for such a nice presentation.
Thank you. Thank you.
Yeah. So our next speaker is Narendra Hegade. He is from Shanghai University, and he is doing PhD with Enrico Solarno. So I request Narendra to share his presentation.
Yeah, hello, can you hear me?
Yeah, it's absolutely audible.
Okay, great. So first of all, yeah, good morning, everyone. And thanks to the organizers for arranging such an amazing event. And also, I'd like to thank Professor Panigrahi for inviting me to give this talk. And I would like to recall that the first QIQT event was held on in 2019, and I was there in Kolkata, and I was also I was in organizing team, and it was on-site event, and it's very fun. So, and it's really my pleasure to be here. So can you see my screen?
Yes.
Okay. Give a second. Okay, so today I will be talking about digitized counter-diabetic quantum computing. It is a new paradigm that we are developing in collaboration with many people from different countries, and it's a combination of three different topics: adiabatic quantum computation, shortcuts to adiabaticity, and gate model quantum computing. And it has in their combination has various applications in many body ground state preparation, solving combinatorial optimization problem, quantum chemistry, solving factorization problems. So there are many, and our focus is mainly on applying these techniques to NISQ devices, I mean noise intermediate scale quantum devices, for useful applications. So basically the main concepts start with the adiabatic quantum computations. Adiabatic quantum computation is a universal model of computing where the solution to a computational problem is encoded in the ground state of a Hamiltonian. And the task is to find the ground state of this Hamiltonian. For that, we follow adiabatic theorem, which says that if you start in the ground state of some trivial initial Hamiltonian, and its ground state can be easily prepared, and if you evolve our system very slowly or adiabatically, you will end up in the ground state of the final Hamiltonian at the final time. So the Hamiltonian describing this evolution is given by this equation, and here lambda is some time-dependent function which decides how do you interpolate from this initial Hamiltonian to the final Hamiltonian. So in principle, any computational problems can be encoded in this way, and we can find the ground state by adiabatic evolution. The time required for this computation and this method mainly depends on the energy gap, the minimum energy gap between the ground state and the first excited state during the evolution. So if the gap is smaller, the runtime is large. If the gap is large, if the gap is smaller, the runtime will be large, and gap is large, then the runtime will be smaller. Generally, for many body systems, with increasing system size, this gap will become very small rapidly. So this will result in a huge computational time. But we cannot do that because of this decoherence effect. If we evolve our system for a very long time, this will disturb our system, and this will reduce the quality of our solution. So the question, however, if we try to evolve our system faster without relying on this adiabatic condition, this will result in excitation between the eigenstate. That also again reduces the success probability of our ground state. So the question is there a way to evolve our system faster? At the same time, can we suppress this non-adiabatic transition or excitations? There comes the topic of shortcuts to adiabaticity or counter-diabatic driving. So this CD driving protocols, these techniques, basically it introduce an additional term to the original Hamiltonian in order to suppress these non-adiabatic transitions. And here lambda dot is tells you that how fast you are evolving your system, and a lambda is an operator, and it's called as adiabatic gauge potential. It is just a name. If you don't like the name, you can call it anything. So this term is mainly this is responsible for all this non-adiabatic transition. So we counteract this term in order to suppress these transitions. So in principle, if you can calculate this term exactly, and if you can implement it, you can evolve our system, your system as fast as and the only restriction is given by quantum speed limit. But in practical, calculating this term is extremely difficult for many body systems because it requires the knowledge of instantaneous eigenstate, or in simple word, it requires knowledge of spectral information of the Hamiltonian, and that is hard. And even if you calculate it exactly, and if you implement it exactly, it's realizing this in the experimental is extremely hard because this operator contains non-local many-body interaction terms, and its realization is experimentally harder. This concept was initially introduced. I mean, this addition of driving term is not a new thing, but this concept of counter-diabetic driving, as far as I know, was first introduced by Demirplack and Rice in 2003. And later in 2009, Michael Berry independently invented this again, and he called it transitionless quantum driving. Okay, so even though the method is useful, which can help us to evolve our system as fast as we want, but it has limitations. And there was various research to approximate this term, to calculate this term approximately and implement it efficiently in the lab. And very recently in 2017, Selvan and Polkovnikov come up with a variational method to calculate these CD terms or this adiabatic gauge potential. And they ask the question, okay, is there a way to construct this adiabatic gauge potential approximately so that we can, its calculation does not require any knowledge of the spectrum of the Hamiltonian. At the same time, it can be implemented in the lab. So they propose this variational method. Basically, we start with some unsatz operator, and it's a local operator. And if it satisfies this condition, we can consider it as an adiabatic gauge potential. And then we try to solve this, minimize this action so that we will get the approximate counter-diabetic term. And later, very recently in 2019, in this PRL work, they proposed the general way to construct this adiabatic gauge potential using this sum of nested commutators. So this combination of these two techniques provide a method to calculate this CD term efficiently without any knowledge of the spectrum of the Hamiltonian, and they were able to speed up the adiabatic process by partially suppressing. Since it's an approximate method, it will not completely suppress these excitations. It can partially suppress this excitation, and it has various applications. So now we have the ingredient. We have a method to speed up this adiabatic process. So how to implement this? So one way is to use analog simulation. So can we use analog simulation? The thing is that no, we cannot, because analog simulation requires, I mean, for this implementation of this counter-diabetic protocol, we need a high controllability. We need orbits. This analog approach does not provide this controllability, and also we cannot implement any arbitrary interactions. And the second approach, can we use quantum annealers like D-Wave? And the answer is no, we cannot use, because D-Wave is a special purpose device. It's designed to only solve certain optimization problems, which cannot implement any arbitrary interaction. Especially there is a class of Hamiltonian called non-stochastic Hamiltonians. This cannot be implemented in D-Wave device. And this non-stochastic, here non-stochastic means these are the problems which face sign problem during quantum Monte Carlo simulations. So these problems are known to be hard, and D-Wave device cannot implement such interactions. So the solution, what we found is that use a gate model approach. So we take this continuous adiabatic evolution along with the counter-diabetic term, and we digitize it using Suzuki-Toda approximation. So basically, we are writing this complicated unitary as a product of simple unitaries, and each unitary in this expansion can be implemented using 1n qubit, 2 qubit gates in a gate model quantum computers. And here in this schematic diagram, you can see how it is implemented in the circuit model. Basically, the qubits are in 0 state, and we start with some initial ground state. Usually it's a product state, for example, which can be easily prepared just by applying some single qubit rotation. And then we evolve our system using this totarized evolution, this digitized counter-diabetic evolution. And each total steps contains 3 unitaries. One is corresponds to this, the problem what we're interested in, the problem Hamiltonian and the initial Hamiltonian, and we have the CD Hamiltonian. So this is the basic of this digitized counter-diabetic quantum computing. And it provides the required flexibility to introduce any arbitrary interactions. It provides the controllability. Also, this method is consistent with error correction. In the long run, if you want to implement it, then error correction techniques are well developed. Compared to adiabatic quantum computing, it is still error correction is still in its early stage. So, but for this gate model approach, we already have this well-developed error correction techniques. And and this concept of digitized adiabatic evolution was implemented in 2016. It was work by my supervisor, Enrique Solano, in collaboration with John Martinez. It is a Google team, in collaboration with the Google team, and it was a digitized adiabatic evolution. And in this work in 2021, we proposed a way to implement this digitized contra-diabetic evolution. You can check it out if you're interested. So moving on to its applications. So we have applied this technique for studying various problems, starting with many body ground state preparation, combinatorial optimization problem, protein folding, portfolio optimization. There are various applications. So I will discuss, discuss about some of the results that we obtained. So in this, so here you can see that we are trying to prepare a GHG state. So the final Hamiltonian is given by this Ising type interaction, where we have this ferromagnetic interaction. And we start with some initial Hamiltonian, which is just a transverse magnetic field. So its ground state is just 0 plus 1 by root 2, or product of plus states. And for this, we use this nested commutator method, what I discussed before, to calculate this approximate contradiabatic term. We add this term and we evolve our system, and we found that the success probability is increased by this contradiabatic protocols. And if you see here we plotted fidelity versus number of qubits, and without adding this contradiabatic protocols, the evolution, the fidelity decreases, and it decreases rapidly. And by including this contradiabatic protocol, we can get better fidelity. And this is the first order contradiabatic term, and this is the second order nested commutator contradiabatic term. And also we studied non-integrable Ising model with up to 25 spins. And the final here, the Hamiltonian corresponds to this model, is given by this ZZ interactions. It's again given by this Ising spin model with ZZ interaction. Also, we have this longitudinal magnetic field along the Z direction. And we start with the, again, this sigma x, this product, tensor product sigma x is our, sum of sigma x is our initial Hamiltonian. And we again calculate this contradiabatic term, and we evolve our system using this digitized contradiabatic protocol. And we see a drastic improvement in the success probability. So here we compared, actually, there are two methods. One is using this variational contradiabatic protocols, and also we use Berry's initial approach, what he proposed, called transitionless quantum driving. And we found that this variational method works much better. And we also operate this for various this many body ground state problem. One is preparation of topological orders, and you can see that even with very small time, we can get a fidelity greater than 95% by including this contradiabatic term. And the second example I'm going to discuss is very interesting. It's related to prime factorization. So it's not Shor's factorization algorithm, it is adiabatic quantum prime factorization algorithms. And here I compare, this is the success probability, and basically the idea is that this prime factorization problem can be encoded in the ground state of a Hamiltonian again. And then we again evolve our system using this digitized contradiabatic protocol. And if you see with this bottom line, without including any CD term, the success probability is much less compared to the this contradiabatic protocols. And we factorize, probably this is the biggest number factorized so far on a gate model quantum computer using this approach. And very soon you will see that there will be another huge news. We are trying to factorize very big number on one of the biggest, one of the best quantum computer in the world. Anyway, so we also implemented this experimentally using IBM device for factoring 35 to 235 using 2 and 4 qubits. And okay, now I move on to the next concept. This contradiabatic protocol, what I discussed earlier, can also be applied to these variational quantum algorithms. And basically in variational quantum algorithms, we have a circuit ansatz and we try to compute some cost function, and we use a classical optimizer to optimize and we update these parameters. So it's an iterative approach. And one such variational method is called quantum approximate optimization algorithm, or QAOA. In QAOA, we have unitary corresponding to the problem Hamiltonian and a unitary corresponds to some initial Hamiltonian. It's also called mixer Hamiltonian. Along with that, we introduce these contradiabatic terms, local contradiabatic terms, which can be easily implemented. And we found that with this addition of this term, we can see a faster convergence to the ground state. And also it reduces the circuit depth by a large factor. Here, P is the number of layers. And by including this CD term, the number of layers required can be reduced. And hence we can reduce the total gate counts or the circuit depth. And we applied this technique for various applications. So here is one example where I applied to this 3 regular max cut, unweighted max cut. And here I show 10 instances and 1 layer. And this orange dots are for this, including the CD term. We call this method DC QAOM, and these blue dots are for this standard QAOA approach. Also, we apply this technique to SK model. It's given by this Hamiltonian, where we have long range all-to-all interaction between the qubits, and Jij can take either +1 or -1, which is chosen randomly from some Gaussian distribution. And we also study various spin models using the same technique, like longitudinal field Ising model, transverse field Ising model, GAG state preparation. In all the cases, we see that this CD inspired approach gives much better result, much better approximation ratio for a fixed circuit. Yeah. And another interesting problem is portfolio optimization. I remember when I was in ISR Kolkata, once Panigraser was explaining how the stock market problem can be encoded in the ground state of a Hamiltonian. That time I didn't understand it clearly, but later I went through in detail, and I also studied this method with our approach using this contradiabatic approach. And we find that so the task here is that you are given a budget. So you have some budget and you want to invest this budget in a n number of assets. So how do you invest in that so that you will maximize the return, at the same time you minimize the risk? So this is the task. So this can be encoded as so this is another optimization problem where you want to maximize the return, you want to minimize the risks, and you have given some constraints like budget constraint. So this can be again encoded in the ground state of some Ising spin glass Hamiltonian, and the contradiabatic approach gives a much good result. And finally, another example is solving application is for solving combinatorial optimization problems. So various industrially relevant applications problems are related to this combinatorial optimization problems. And we studied that, especially you can think of this D-Wave device. What they solve are basically these combinatorial optimization problems, where they encode this optimization problems in the ground state of some classical Hamiltonian. It's a classical spin glass Hamiltonian, and this Hamiltonian is stochastic. When they evolve, there's this quantum annealing. What they're basically doing is a stochastic Hamiltonian, and it is believed that stochastic Hamiltonians are not powerful. They can be simulated efficiently using Monte Carlo techniques. So there is a belief that this non-stochastic adiabatic quantum optimization is much powerful than the stochastic optimization. And we show that using this non-stochastic counter-diabatic protocols, we can achieve a polynomial enhancement in the ground state success probability for this Ising spin glass problem, which are in the worst case, this finding the ground state of this Hamiltonian is a NP hard. So we show that these non-stochastic CD terms can give polynomial enhancement compared to quantum annealers, the existing stochastic quantum annealers. And finally, when we studied why it is giving this polynomial enhancement, we studied this energy gap. And we found that inclusion of this CD term increases the energy gap. So as I discussed earlier, if the energy gap is larger, the runtime is smaller. So that is the reason behind that. And finally, we implemented this on trapped ion quantum processors provided by this Quantinum or Honeywell with up to 6 qubit. We study here. I show the example of 5 qubit system, and we also implemented it on IBM quantum processor, superconducting quantum processor, and we found that the ground state can be obtained with very high success probability with this contradiabatic approach. So to conclude, this DCQC approach, this digitized contradiabatic quantum computing approach, has various applications, starting with many body ground state preparation, combinatorial optimization problem, solving factorization, linear system of equation, and it is just a beginning, and we are still exploring. There are many open questions. There are many unexplored things out there. So I highly motivate you to look at our works. And also we applied this contradiabatic approach for this hybrid quantum classical algorithms, where this CD inspired approach provides you faster convergence with reduced circuit depth. And another approach that we are working since many years is called digital analog quantum computing. So digital analog approach is different from the standard universal quantum computing, where you have this standard quantum gates like C0 and rotations. But if you want to, that is for fault tolerant quantum computers. If you want to achieve something useful in the NISQ era, we have to try a different approach. We have to dig deep into the hardware, and we have to see what are the native interaction available. Because implementing with native interaction is much more efficient than using the standard gate-based model, using the standard logical gates. So that is something we are trying, and we call this paradigm NISQA, that is achieving noisy intermediate scale quantum advantage. We call this in short NISQA. So to conclude, thank you for your attention. If you have any question, please call, please ask here. And also I want to advertise that we are starting actually we are opening a new startup in Germany, in Berlin, called Kipu Quantum, and we already started hiring. If you are interested, please go to this website and you can directly apply. So yeah, thank you for your attention. If you have any questions, please ask.
Okay, thank you, Narendra, for your excellent presentation. So if there are questions or doubts, please. Yes, sir, please.
Yeah, Narendra, excellent talk. And I have a few questions. You looked at this some of these spin models.
Yeah.
Am I audible?
Yeah, I can hear you. Yeah.
Yeah. So this, what is the idea behind this factorization? What happened? Just tell me about this factorization. I'm a bit curious.
Okay, so let's say n is the number we want to factorize, and p and q are its prime factors. So we represent this p and q as in the binary rotation. Let's p is equal to x1, x2, x3 up to xn, and q is equal to y1, y2, y3 up to yn. Then we multiply this p and q. It's a binary multiplication. After multiplication, we will get a set of equations. We call it factorization equations. So its equation consists of all these binary variables, and we minimizing these equations will give the solution to p and q. So this minimization can be encoded in the ground state again. Ground state of Ising Hamiltonian.
Okay, got it. Yeah.
Yeah.
I have a question here.
Yeah.
Suppose you want to factorize the number n, and you are saying that its prime factors say p and q. So how do you determine that p and q the prime factor? There could be another pair of prime factor, or how do you determine that p and q is the prime factor?
Okay, so we are basically considering this prime factorization which only has two prime factors, a number which only has two prime factors, and we represent this we represent this prime factor P is equal to some variables in terms of some variables in binary variables x1, x2, x3, x4. We don't know its value, we don't know its length, we don't know anything about that. We are assuming that yeah, it is a binary. We can represent in a binary notation. The numbers can be represented in binary notation. We encode them in the binary variables, and after representing this, we multiply these two binary variables. So we will get a set of equations. It will be some of x1, x2 like that.
Yeah, combination of x and y's.
Yeah, combination of x and y's.
Okay.
Then it will reduce us to minimization problem, minimization of some Hamiltonian. It's basically Ising Hamiltonian. It's a 4 localizing Hamiltonian. It reduces to minimization of 4 localizing Hamiltonian. And what we don't know is that Shor's factorization algorithm provides that's the polynomial enhancement. It's easy to prove that prove the polynomial enhancement, not polynomial, this polynomial runtime, not the polynomial, it's the exponential enhancement. So this polynomial runtime can be easily proved, but for this adiabatic algorithm, still it is don't know. It's a very difficult problem to calculate this computational complexity, the time required for the runtime, because it mainly depends on this minimum energy gap. If this gap scales polynomially, the runtime is also polynomial. If this gap scales exponentially, the runtime is exponential. And determining this gap for larger systems is extremely difficult. We don't know how to generalize it.
Okay.
But yeah, but with our approach, even very big numbers can be factorized on existing noisy quantum computers.
Okay.
Yeah.
Yeah. See, I have a related question to Priyam.
Yeah.
See, for example, if you really have two different independent factors, what happens? It will settle down to two ground state kind of thing, or
if you
suppose you have two independent, prime factors.
Yeah.
So what happens when you evolve? What will be the result?
So you are saying that there are two results. There are
That's
two. Right. Then the ground state is degenerate. The ground state will
correct.
Yeah.
Okay.
Yeah. Still we can back up. Yeah.
So is there any other questions? Okay, if there is no other questions, let us thank once again the speaker for his excellent presentation.
Yeah, thank you so much.
Yeah, so our next speaker is Sumit Mukherjee from NIT Patna. So Sumit, please share your talk.
Yeah. Is it visible? Hello.
Yeah, your presentation is not visible. I think you shared. Yeah.
My screen is visible, right?
Yes, your screen is visible.
Okay.
Yeah.
Yeah. Now my screen is visible, right?
Yeah, it's absolutely fine.
Okay. So
Sumit, please continue.
Yeah. So thank you. Yeah. So first of all, I want to thank Panigrahi sir for inviting me to present our work. So here I will not really present the whole presentation. Is not our works, but I will motivate you with some foundational questions and will try to give some answer. So there is a common perspective that quantum states, or it is a fundamental notion, it is contained in quantum theory, that two quantum states, non-orthogonal quantum state, cannot be discriminated with 100% probability. It is already known, and it is related to some other fundamental notion called no cloning theorem and all. But you all know that if you try, you have some strategies with which you can discriminate two states at least with some probability, and it has a very good application in the quantum information processing task. Many of the information processing to discriminate two states, it has importance. So a common perception is that quantum theory, in quantum theory, the probability of discrimination is maybe the less. In classical theory, we can discriminate two states with more probability than quantum theory can do. I mean, using the quantum tools. So, is it true or not? This is my question, or main fact of my representation. So, I will raise some questions and then try to answer some of them. So, for the presentations, to know the question, even we have to go through some basic things which will help us to understand what am I meaning by classical theory and quantum theory. This distinction is needed, so that I represented it, as you can see in the slide, that I represented two different world views. This is coming from the classical philosophy of epistemicity or epistemology. So there are many world views. You may have your own world view, but according to classical philosophy, there are some different world views. So two of them I enlisted here. One is empiricism, another is rationalism, and they are in contradiction with each other. So they say the origin of knowledge, how the what is the origin of knowledge. So empiricism, they say that knowledge is built upon our sensory experiences. What we experience in our everyday life, from there the knowledge comes. And another branch of these theories, they say, who are rationalists, so they say no, there is nothing to do with this everyday experience. Only with the rational reasonings you can come up with your world knowledge. And also there are a class of theories in the empiricist class. They are operationalist, and another in this rationalism class, they are realist. So our main goal is to understand who they are actually, this operationalist and realist, because it is needed for our discussion. So operational in an operational theory, who are operationalists, their goal is to figure out the experimental result with some theory, only the experimental result with some theory properly. So they don't want to know anything about what is happening behind the scene. They have an experimental setup in lab. They have some statistics they get from the experiment, and from their theory, they will explain how the correct probability of the statistics. I mean, correct probability which is occurring in the experimental lab. So, but the realist's goal. So I will come later what realist goal is. So first of all, what operational theory consists. So a operational theory consists of three things like preparation, transformation, and measurement. You can relate it with your quantum theory, because quantum theory itself is an operational theory. And in quantum theory also, you have preparation, transformation, and measurement. So how they are? In quantum theory, preparation is represented by state vectors, or more generally by density matrices. In transformation, by some unitary evolutions, and measurement by positive operators. So now the role of the realist comes. So in in quantum theory, say, see the picture depicted here. So in the picture, you can see a simple setup which you know from your textbook quantum mechanics. That is a Stern-Gulak setup. So suppose that psi is a superposition of some states, say 0 plus 1 by root 2. So your quantum theory gives a Bond rule to you, that you know that Bond rule predicts the probability of a certain event, but it will not say anything about the how this probability is coming. So just think about this apparatus. So if I say a superposition state 0 plus 1 by root 2, or say 5 plus or 5 minus by root 2, 1000 electron in this state I send through Stern-Gulak magnet, you will, from your Bond rule, you will always predict that approximately 500 will go up and approximately 500 will go down. But if I ask you, and quantum mechanics rightly predict these things, in subatomic range, every experiment that is being conducted on Earth, it satisfies this Bond rule. Nowhere it is saying that Bond rule fails. So you don't have any doubt, you should not have any doubt with quantum theory. Quantum theory is predicting the statistical results precisely. But now if I ask another question to you, that I will send 1 electron, not 1000 electron, 1 electron to the Stern-Gulak magnet, and I will ask you, you just predict where the electron will go. Can you predict? So simply this answer is no. Quantum theory do not give you any tool that will predict where a single electron will go, either up or down, in a single short experiment. So this is the limitation of quantum mechanics. So if you are a realist means you want to know the description of a physical particle at every instant of time. You not only want to know the statistics, your goal is to know at event by event description of a physical system. So if your goal is this, then you will say that, oh, quantum theory is not giving this one. So quantum theory is not a complete theory. So I should make another theory which is compatible with a realist view or daily life view, and also reproduce the quantum theory, the Bond rule. So because Bond rule, at the end of the day, for subatomic phenomena, explaining subatomic phenomena, we have to reproduce the quantum mechanical Bond rule. But we also want a realist, we also want a more intuitive description of nature, right? So that is a realist view. So Einstein, I show you in the picture previously, Einstein was a hardcore realist. And this Bohr, Niels Bohr, you may have heard some debates on Bohr and Einstein's letters. So Bohr was an operationalist, you want, and his follower was also operationalist. They only want the experimental result to be true with some theory. They say that just experiments were just sort of and calculated. If it is describing rightly your view, I mean experimental statistics. So, but the hardcore realist will not agree with that. So Einstein was a realist, and he defended the realist view till his death. So there are some views what reality is. I tried to mention here. This is exactly what Einstein said in his paper. I just copied and pasted it here. And this is Bayes' view. So Einstein's view was that if in quantum mechanics says, when you are observing, you are not observing anything, there is no result. Jordan said it quite before in 1930s. But Einstein says, well, what is the reality? Reality is, if without disturbing a certain system, you can predict with certainty the state of the system at every instant of time. So that will be your statement of reality. So if I want to develop a theory which is a real theory and will reproduce quantum mechanics, so that real theory should have this characteristic. In that theory, every physical quantity should have been extracted. The knowledge from that quantity should have been extracted without disturbing the system. So there is an Bayes' view that is not exactly what he told, but what is known from his work, that is written here. And there are some other views on macro realism that is inspired from our everyday views that macroscopic objects has a definite state at each instant of time. So I'm not going into the detail. This has a very deep implication in foundation of quantum mechanics, but I'll just tell you the tools. So now I want to develop a model which reproduces quantum mechanics and also is the step-by-step description of a physical system. So here you can see that model. We call this model as an ontological model. Ontological model. So you can relate it by your classical notion. I mean, you all know classical mechanics. So in classical mechanics, the trajectory of a particle is defined on a phase space by x and p two variables. So if we have some other quantity in classical mechanics like energy and angular momentum and all these things are just a function of phase space. I mean, if you know the phase space trajectory, you can calculate everything, energy or Hamiltonian anything. So in an ontological model, we should have such a variable that will explain the time by time evolution of the system. So we say that variable is lambda, and if by knowing lambda for a certain state, if we know the lambda, we can give, because see, we have a state and we also have a lambda, then we have both the requirements satisfied that we can now reproduce bound rule, and if we know lambda, we can give step-by-step description of the system. So my general theory will be more general, I mean more complete than quantum mechanics, and it will satisfy, it will actually predict all the subatomic experiments. So this theory is formed like this. You can see whenever you produce, think it like this, that whenever you produce a system and you represent it in your quantum mechanics by a psi, correspondingly, the theory you are making, in that theory, in the lambda space, one probability distribution that is called mu psi lambda is created. So for a certain lambda, one or the other, for a certain state psi, one or the other lambda will be created for sure, because your basic assumption is that. So that this whole probability sum up to 1. And as it is a, I mean, operational theories, realist description. So we have transformation and measurement. Though for the simplicity, I am skipping the transformation. I only have written here the measurement. So in the measurement, you can see you have, like in a quantum mechanics, compared with your quantum mechanics. In your quantum mechanics, you have positive operator value measured. Here, you will have some response function. We call it response function. This response function will give a response for a certain state psi. So now come up to this definition. So at the end of the day, our goal is to reproduce quantum mechanics also, unless there is no meaning of finding an ontological model. So the probability for a certain outcome, for a certain preparation, should reproduce the quantum mechanical statistics. So that is our bond rule. Say you produce a state psi and you want to know what is the probability of getting phi k. Phi k is a certain outcome. So this is bond rule predicts psi phi square, mod square. So in the ontological model, now just think, just see the integral. See, you produce a state psi in your lab. For that, a lambda is created. For that lambda, what is the probability of getting a phi k? That is given by this response function. So this is just the product of two probabilities. This will give you the bond rule. So now see, I assume you succeeded to construct a theory which gives a realist description. And this report, whether all the statistics in the operational level is reproduced by the theory, that is another question. So that will come later. But say you construct such a theory, an ontological theory. So now a very vital question arises. So in operational level, say the symmetries or anything, any property you observe in operational level, does it reflect to the ontological level also, which you are predicting? It is not a priori clear. You cannot assume it. If you assume it, then it is an assumption you should say. So such a question, such a particular question arises when we want to describe, I mean, that is how we describe the notion of contextuality. So what is that? So there comes the Leibniz principle of indiscernibles. So that is that. It is also a classical philosophical notion that when two objects are different, so this principle says that there cannot be separate objects or entities that have all the properties are in common. That means, conversely, I can say that if two objects have all the properties common, then the entities are same. So you just see this. I have written it this common and same in two different colors to make you inspired why this is so. I mean, you will think that common and same are same thing, but it is not true. Say if two objects have all their properties is common, how do you know it is common? You have to do something experiment. So it is a operational. I mean, I wanted to mean this common as an operational word. So you have performed an experiment on two different systems. You see that this two system has all its properties common. Then you will say, okay, if for this experiment I have a realist theory, in that realist theory also, these properties will be the same. All its properties will be the same in the ontological level also. So if I assume this assumption is itself called preparation contextuality. I mean, it is inspired from this. It is preparation non-contextuality assumption is inspired. So what it says in a real experiment or in your lab, if you have, I mean, with all your resources, all your measurements, if you cannot distinguish two things, I mean, say I prepare, it will be more clear if I go to quantum mechanics. So say you are producing one state psi with two different procedures. You can always make it. Like just consider the identity by 2. You can produce it by 0, 0 plus 1, 1 decomposition or plus, 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 minus, minus by 2 decomposition. But the same state is produced by different preparation procedures. But can you distinguish this state? These states cannot be distinguished in quantum mechanics. You can perform any, I mean, in the scope of quantum mechanics, you can perform any experiment. If you cannot distinguish the preparations with which this state is prepared, then the question now arises whether this same notion is valid in the ontological level. If you assume that yes, this notion is valid in ontological level too, then you are assuming preparation non-contextuality. That means you are saying that with which preparation it is prepared, one state is prepared, psi has lambda has nothing to do with it. Lambda only knows what my rho is. With what procedure this rho is produced, lambda has nothing to do with it. So this is a preparation non-contextuality assumption. This is you can see the reference. If you are interested, this is a very good paper by Robert Spekin, 2005. You can read this paper. So first, this assumption was shown in this paper, and there are some other contextuality assumption which I am not going into the detail. So, so now I am coming to a quantum mechanical task. So whether two non-orthogonal quantum states can be distinguished with certainty. So the answer is simply no. You all know. But there are some, as I have already said, that there are some methods or some schemes in the scope of quantum mechanics with which you can discriminate two non-orthogonal states with at least some probability. Some of them are I have enlisted here unambiguous discrimination. Here, what this is depending upon your experimental requirement. You say from many states you want to extract out one state, so there should not be any ambiguity in judging the state. So in that, while the requirement is something like that, so we will employ unambiguous discrimination. When we have some other things, say we allow error, but we want to discriminate two states. So that time we employ minimum error discrimination strategy. So in minimum error discrimination strategy, we just want to minimize the error. I mean, say we have two states. For the first detection, I will assume this state is Psi1, and for the second detection, I will assume this state to be Psi2. So sometime it will happen that it will be jumbled up, like Psi2 is coming in the first detector and Psi1 is coming in the second detector. So it will be caused as error. So this error in the minimum error discrimination, your strategy, your goal is to minimize this error. So there are quantum strategies. I will not go into the mathematical complexities and the technical things in this talk. So that will be really very boring. So, but if you are interested, we just note down the references you can see from there. So now a task, say I am defining a task of two-state discrimination. So this is a very well-known bound. This bound is given by this Hailstrom. It's a very old paper. So in measure theory, if you read, then you can find this bound. What is the maximum probability of discriminating two states? Here P1 and P2 are the prior probabilities with which you are sending the states. And C Psi1, Psi2, what you are observing, it is just the overlap between the two states. It is, we will call it as confusibility. That means with this amount, with this probability, you are confused what the state is. The overlap is actually the quantitative description of this confusibility. So these are actually the probability what we calculate in different stages discrimination tasks. So we will only consider the minimum error state discrimination and maximum confidence discrimination. So in the maximum confidence discrimination is done when your states are linearly independent. So in the linearly independent states, you don't have the provision to do unambiguous discrimination. So here we employ maximum confidence discrimination. So these are the probabilities for that. So now come at the classical strategy. All mathematics written here, we get it from quantum mechanics. So as we are interested, if we are a realist, so we have this realist model. So in that model, there will be strategy to discriminate two states. So now, what will be the strategy for these states? State discrimination in classical mechanics. So say we have two states, Psi1 and Psi2, and they are producing two lambda distribution, lambda Psi1 and mu lambda Psi2. So we have to discriminate a certain lambda. I mean, because we want to know the lambda, the characteristic of lambda. So in a classical strategy, our goal is to find out where from each lambda is coming. Either it is coming from mu Psi lambda or mu Psi2 lambda, Psi1 lambda or Psi2 lambda. So our main goal is to detect from where a certain lambda is coming. So I am just denoting one certain lambda by lambda star, and we will have to take this strategy for all lambda. So this success probability becomes this. So main goal is that, say I have given you one lambda and I ask you from where it is coming. So simply you will, if you know which has greater probability, you will just predict that one. So our main task is to find whether this probability, this first probability or second probability is maximum. So this is the main task. And if we know that, we can just simply substitute that one into this expression number 4, and we'll get a success probability in classical model. So it is a classical model. Only I have not taken any assumption about the non-contextuality, what I described you earlier. So now the non-contextuality assumptions coming up. So that is, I told you that an identity by two state can be formulated, formed by two different experiments, say two different non-orthogonal compositions, non-orthogonal vector compositions. So they are indistinguishable in quantum mechanics. Now I am assuming they are also indistinguishable in classical theory, which I am constructing. And for that, we also made it intact. This convexity property made it intact. Like you can see that this convex combination is also reflected in the this release description. So we assume that these two, the states formed, which look similar in quantum theory, look similar in an ontological model. So this is our non-contextuality assumption here. So if we impose this assumption in our this fourth equation, this has some mathematics you have to go through. So I'm not going into the detailed mathematics. So if you impose this restriction in that theory, you will come up with a bound success probability in classical theory, or rather I will say it is a non-contextual classical theory. Classical has different meaning. It is very vague, the term classical. So from here on, wherever I mean I'm using the word classical, you will just think that it is a preparation non-contextual ontological model. So in a preparation non-contextual ontological model, a success probability of state discrimination looks like this. S equals to this bound. So this is first predicted in a paper, 2018 paper by Robert Spaken. It is given in the reference. So they used the prior probability of sending these two particles, these two states which you are discriminating, with same prior probability you are sending the states. They have not considered what happens if different success when different prior probability with different prior probability you send this states. So this is actually very intuitive. If you send two different particles, we saw that two different particles with different probability, we saw for all the prior probability range, their argument is valid. I mean, quantum theory is always better performing from the classical one. See, this is a classical probability, and in the graph you can see this non-contextual bound predicts this one, and quantum theory predicts this one. So quantum theory always discriminate with a better success probability. So this strike to your intuition. You assumed that okay, my classical in my classical theory, the state will be more distinguishable. But I strike to this notion that I will give you one classical theory where compared to that, quantum theory will perform good. So now, question arises whether this is valid for all prior probability. So we see that it is very simple. We see that yes, for all prior probability, all the range of prior probability, this argument is valid. So you can see that these extreme points, they actually reproduce this second phrase. So for any prior probability you send to this particle, quantum theory is always perform good. So now a further question arises whether this is true if you increase the number of states, because for the experimental requirement you may have requirement to discriminate more number of states. So whether in that case also you can use preparation contextuality as a resource. This question arises. So whether what happens if I go in a task where more states are involved. So one thing I want to tell you that as you increase the number of states, there is no general strategy. There is no general strategy with which employing with you can discriminate 3 or more quantum states. But if the states has some particular symmetries and all, you have some strategies in your hand. So let us consider 3 different states which are mirrored symmetric states. It has some mirrored symmetry. Like if you some transformation, give some transformation which makes 0 to 0, make transform 0 to 0 and 1 to -1, this whole set of state will be unchanged. So this is called a mirror symmetric state. So for that you have a quantum strategy with which you can discriminate this. It is represented in block sphere, you can see here. So we calculated the quantum success probability for this discrimination task was known, and it is like this. The mathematical picture is like this. You can see from this paper also how these things are employed. So now, what happens in our classical theory, the preparation non-contextual theory? So we calculated the bound is like this, and from the picture it is evident. You can see that this green is for quantum region, the upper bound of quantum success probability, and this one another color is for the classical success probability. So you can see for all the range of prior probabilities, the previous argument was not true when there are more states than 2. So you can see I can also discover some state for which quantum theory actually perform worse than this classical theory. But we found some region, I found some state, and with which some probability combination, if you employ in an experiment by maintaining this prior probability, you will get advantage for sure. So this is given in the this green region. So we also extended this notion to maximum confidence discrimination. So we calculated the quantum bound for 3 mirror state discrimination. We see that this bound comes to be like this, and for non-contextual theory, this bound comes to be like this. You can see in maximum confidence discrimination also, the physics is valid. What I was describing in minimum error discrimination, that you will get some restricted region in where you will get this quantum contextual advantage. Quantum mechanics will perform good than a non-contextual theory. And this graph represents a very special set of states that is called the trine states. You will use in many of the information processing tasks these states, trine states. So here you will see that quantum theory is always performing good in the case of maximum confidence discrimination. But whether you can extend it for a further complicated setup or further complicated task where more states are involved and more complexities are involved, that is not a priori clear now. This will be a future direction for the researchers. So these are the conclusion. Conclusion I have already told you that while I am giving the talk. So these are some conclusions, and extension which I was referring again and again, these results. If you want to have a look at it, what is the motivation and all and mathematics, then you can look at this paper. But this paper is this archive version. But this archive version is a very rough version. You can actually contact me if you have any further questions on this. Thank you.
Okay, so thank you, Sumit, for this such a wonderful presentation.
Yeah, thank you.
If
anyone has some questions.
Is there any questions from audience, please? Okay, so if there is no questions from the audience, let's thanks to our speaker once again.
Thank you. Thank you.
Okay, so our last speaker for this session is Vaisakh Mannalath from Jaypee Institute of Information Technology. So Vaisakh, yeah. So Vaisakh is going to talk about bounds on semi-device independent quantum number expansion. So Vaisakh, now
Yeah,
it's
yeah, I hope you can hear me now.
yeah, your voice
Yeah.
is visible, slides is fine.
Okay. So, first of all, I thank the organizers for giving me this opportunity. And today I'll be talking about some results that we obtained on semi-device independent quantum random number expansion. So, first of all, let me explain why we need quantum systems for random number generation or expansion. So, traditionally, how we generate random numbers, let's say in a computers or in other simulation softwares, is by using classical deterministic algorithms. So, these algorithms take an input random seed and then use some properties of number theory to generate random seeds. So first, if we know the initial random seed, then the output will also be completely predictable. So this forms a security crisis, and this is why you use quantum systems to generate random numbers. So there are many ways to generate random numbers using quantum systems. So if you think about let's say a quantum state in equal superposition of states, and you perform some basis measurement, you'll get the outputs in an equiprobable way. But there is no way to certify that what we are actually producing is random or not. Maybe the state that we are producing is not an equal superposition. Then how do we know that whether the outputs that they produce is inherently probabilistic or some defect of the device that we have manufactured or bought from a third party? So the device independent method is a way to certify the random numbers produced by quantum systems. So first our results are on semi-device independent random numbers, but first let me give you a brief background on device independent models. Okay, yeah. So in a device independent model, we have two parties, Alice and Bob. So Alice and Bob will share a entangled state or Bell state, and they will each get a random input state X or Y. And based on this inputs, they perform some measurement on their part of the system that they're sharing and produce a random output A or B. Right. And this is not the entire protocol is known as quantum random number expansion, because the Alice and Bob needs input random numbers to set their measurement settings, right? So they have some input random number and they produce some measurement based on those random numbers and produce an outputs A and B, which are indeed random again. So the way they certify this entire protocol is using some correlation function, probability correlation functions shown here as an I. So you can think of it as the CHSH function. So from the probability distribution that they obtain, they will perform some calculation and get an output number. And this output number will have a classical threshold value above which we can be sure that the protocol that they are performing is of a quantum nature. And this is how they wish to certify their outputs based on the output value of this correlation function. But this device independent model have some drawbacks. The main drawback is that it requires non-locality, in the sense that the research into the device independent model has been going on for about more than a decade right now, and still device independent models are still in the laboratory settings. There is no commercial product that we can buy or off-the-shelf products that employ this device independent model generating quantum random numbers. And also, since the protocol requires non-local resources, the generation speeds of the devices are also slow. So is there any way that we can bypass this requirement of non-locality? Well, actually, there is no real way. Anyway, so the device independent model is the most secure quantum random number generator available to date. And in order to bypass this non-locality requirement will be to forsake some of the security that the non-locality produces. So only way to increase the, let's say, the generation speed is to get rid of non-locality. And by getting rid of non-locality, we'll lose some of the security that it provides. But nevertheless, if we can suppose, let's say we are manufacturing a device on our own, and maybe we can trust some part of our devices more than others. So maybe we can leverage that to produce a entire device which is less secure than the device independent model, but nevertheless can be used for practical purposes. So for that, we make some assumption about the device. Suppose, let's say the measurement device of our entire device is well characterized. Maybe we can trust the measurement device, or maybe we can trust the preparation device, the device that is preparing the quantum states. Or in our case, what we've done research on is we make an assumption on the dimension bound of the system used. So we use the protocol, we consider a protocol in which the dimension of the system is bounded. So we use two-dimensional system to generate to create a protocol which is less secure than the device independent model, but given the assumption that the assumption is true that the system is using a two-dimension to have a two-dimensional space, then this device is this protocol is as secure as the device independent protocol. Right. So this is the semi-device independent model. We have a quantum source, and the quantum source gets an input state x, and based on this x, the source produces quantum source produces a state rho x, and it sends to the measurement device. And the measurement device will also have an input state y, and based on this y, it performs some measurement on the incoming state rho x and produce a random output b. So this is the b is our random output. The objective of the protocol is to certify the randomness of b given some probability distribution that we obtain from this protocol. So as I said before, in some semi-device independent protocol, the quantum source is well characterized. In some device independent protocols, the measurement devices are well characterized, and there are even protocols in which there exists a bound on the energy of the state sent from source to device. So in our protocol, we are using a dimension bound restriction. So the certifiable randomness is obtained based solely on the input output statistics with an additional assumption of the dimension bound. Right. So the motivation for this work comes from the device independent scenario. So in the device independent scenario, people have already proven that if you are using a local two-dimensional system, the maximum certifiable randomness that you can obtain is 2 bits. Okay. And since this is a quantum random number expansion scenario, the input settings are also of relevance here. So the input settings should also be random. So if there are research that proves that if there is any bias in the input settings, that can be used by an adversary to predict our random outcome. So this input randomness is also an important resource that we have to take into consideration. So people have conjectured that in order to generate this maximum randomness of 2 bits, you need the minimum is conjectured to be 7. So this input settings includes both settings given to the preparation device as well as the measurement device. So in the semi-device dependent model that we are considering, we need to answer similar questions. So as in, what is the maximum amount of randomness that you can certify in a semi-device dependent scenario, and what is the minimum number of input settings required to generate this much entropy or randomness? Right. So this is the model that we're considering. As we've seen before, there are 2 black boxes, A and B. So we don't know what's going on inside these devices. We just know that we are giving these devices some input settings X and Y. And based on X, A sends the state rho X to B. B performs measurement based on Y and produce an outcome B. So this entire protocol can be characterized using the probability distribution PBXY. So if you're using a quantum system, this PBXY is calculated using the bond rule trace of rho X measurement density states and the measurement operators. Right. So given the probability distribution, how do we distinguish classical two-dimensional system versus quantum two-dimensional system? So remember, in our model, the only restriction is that the system sent from A to B, the rho X sent from A to B is two-dimensional, but it can be classical as well as quantum or anything in between. So how do we distinguish classical versus quantum states? So here we use the concept of dimension witnesses. So dimension witnesses were originally introduced as a way to certify whether the protocol in consideration use to produce an upper bound on the dimension of the system used in a particular protocol. But since we are restricting ourselves to the two-dimensional case, it can be a way to distinguish between the classical two-dimensional and the quantum two-dimensional. So dimension witnesses are linear functions of the probability distribution. So Pxy is the probability to get outcome 0 given xy, and Wxy are some real coefficients. So for some certain well-chosen dimension witnesses, there can be for some protocol we can have a dimension witness that are well chosen, which can certify the randomness of the output of the measurement device. So in an experiment, we will observe this dimension witness W, and whenever the dimension witness W is greater than the classical upper bound on this dimension witness, we can be sure that there is some quantum nature to the protocol that we are performing in our lab. So WQ is the quantum upper bound. Okay. And how do we measure the randomness of the output B? So in our work, we use the minimum entropy function. So the minimum entropy function is defined as way, and it is taken as the negative log of the most probable event. So this BBXY is the probability to get B given XY, and it is maximized over all BXY, all the parameters BXY. So this is the most probable event, and this is the most conservative way to define an entropy of a protocol, because if you, let's say, suppose you take the average over the entropy of the outputs, this will definitely be lesser, greater than the minimum entropy function. So this is the most conservative way to measure the entropy of a protocol. So any other entropy measure will be greater than this minimum entropy function. So certifying this protocol means finding this minimum entropy H infinity given W, the dimension weakness, the observed dimension weakness. So now we need to maximize this minimum entropy H infinity. So maximizing this H infinity means minimizing this most probable event. Since if you remember, the minimum entropy and the most probable event are connected by a negative log. So maximizing one means minimizing the other. So for minimizing this most probable event, first we define a quantity known as PLB. So PLB, it has a maximization over X. So X is the preparation settings, Y is the measurement settings, and B is the outcome. So PLB has a maximization over preparation and the outcome, but it has taken an average over all the measurement settings. So this will definitely be, this quantity PLB will definitely be lesser than the most probable event, since here we have a maximization over measurement settings, and here we are taking the average. So which means that if you take an average over a particular set, it will be definitely be lesser than the maximum of that set. So finding the minimum value of this most probable event boils down to finding the lower bound for this PLB. Right. So now we try to find the lowest possible value for this PLB value. So minimizing PLB. We use block sphere vectors to represent the measurement and states. So we are only considering pure states and projection measurements, because in the case of randomness expansion, in two-dimensional system, we need only consider those. And to satisfy this maximization over all X, the preparation settings, the state is taken to be along the average direction of the y directions. So here we have an average over a measurements, and in order to maximize this preparation condition, we need to take the vector of the block sphere vector of the state, prepared state, to be along the average direction of the measurement basis vectors. So I'll clarify what I mean by taking the average direction. Suppose we have two measurement settings, so y equal to 2. So shown here is some equatorial plane of the block sphere, and we have two measurement bases, T1 to minus T1 and T2 to minus T2. And now we need to find a state which maximizes the preparation settings, maximizing this value here, this maximization, right? Since we have a maximizing over B in the PLB condition, we need to take the quadrant. So this measurement basis will form 4 quadrants, and we need to take the quadrant forming the least angle between them. Right. So there will be 2 quadrants forming the least angle. So in this case, it will be this quadrant and this quadrant. And the preparation state that maximizes this average will be the state that lies along the average of T1 and T2, or minus T1 and minus T2. So any of these choices are equivalent. So we choose along the positive direction. We choose Sx to be the normalized vector along the sum of T1 and T2. So this prepared state maximizes this value here. So this was the case for 2 measurement settings. So for measurement settings greater than 2, we have a similar form for the prepared state vector Sx. So you'll take this form, and this maximizes this value here. So if you take this Sx, this gives us the PLB value. So PLB again, as if I say it again, if it's the maximization over measurement settings, taking the average over the measurement set, okay, maximization over the preparation settings, average over the measurement settings, and the maximization over the outputs. And PBXY is the half for 1 plus Xx dy. So in the block sphere representation, we can get the probabilities in this form. And Sx, as we found out now, should take this form when the T1 to Ty are the measurement vectors. So we put it all together into PLB, and we obtain this form for PLB, half into 1 plus norm of the sum of measurement vectors by the number of measurement settings. So this norm is minimum when the vectors are the farthest apart. So since we are dealing with two-dimensional system and the block sphere takes a three-dimensional form, the vectors, the norm is minimum when the vectors are equally distributed along the 3D axis, and the number of vectors are a multiple of 3. So putting these two conditions, that is, the vectors should be equally distributed along the 3D axis, as well as the number of vectors should be a multiple of 3. We get a lower bound for the PLB value, which is half into 1 plus 1 over root 3. And taking the negative log of this gives us an upper bound on the minimum entropy H infinity, which turns out to be of this value. So we have now found the maximum entropy that you can extract from a two-dimensional system. And the number of measurement settings, as we said before, is should be a multiple of 3. So the lowest multiple of 3 is 3 itself. So the minimum number of measurement settings required to generate this much entropy is 3. So what about the minimum number of preparation settings? Okay, so it can't be 1 because that's a trivial case and there is no separation between classical and quantum systems if the preparation settings is 1. It can also not be 2 because in the worst case scenario, for two-dimensional systems, 2 states are always distinguishable. And we have proved that it can be 3 either. So we converted a protocol with 3 preparation settings and 3 measurement settings into an quantum random access code protocol. So I will not go into detail what I mean by quantum random access code protocol, but just know that any protocol with 3 and 3 settings can be embedded within this protocol. So shown here is the block sphere diagram of the protocol, and the black vertices are the encoded states. So they are represented using these 3-bit strings. So any 3 prepared settings can be taken to be some combination of 3 vertices among these 4 vertices. And the 3 measurement settings are shown with these arrows. So arrows are the up axis of the measurement basis. So if you perform this protocol, you'll get an average success probability. And turns out the average success probability of this protocol is greater than half into 1 plus 1 over root 3. And since the maximum of a probability distribution is greater than the average probability, the extractable entropy from any such protocol will be less than the optimal value that we derived earlier. So we proved that we need more than 3 preparation settings to generate the maximum entropy. And now we give an example of a protocol with 4 preparation settings and 3 measurement settings. So again, shown here is the block sphere structure. The black vertices are the prepared states, and the arrows indicate the axis of the measurement. We see here that it's a very symmetrical structure because the black vertices occupy the alternate vertices of a cube inside the block sphere. So this prepared states form a regular tetrahedron inside the block sphere. And the arrows, if you extend along negative and positive direction, forms the vertices of an octahedron. So it's a very symmetrical structure. And this is the dimension witness that we use to certify this protocol. So the vertices are indicated using strings to compactify this notation here of the coefficients. And this dimension witness has a classical bound of 3 and a quantum upper bound of 2 root 3. And we have derived an analytical relationship between this dimension witness value R43 and the minimum entropy. And we found that whenever the dimension witness value is greater than 3 and less than 2 root 3, we have non-zero minimum entropy, which means that the protocol is very noise robust as well. And so in conclusion, we derived the maximum amount of certifiable randomness from a qubit. We derived the minimum number of input settings to generate the maximum amount of entropy or randomness. And we showed the existence of a protocol that matches these bounds, which means that this is the most efficient randomness expansion protocol for a qubit system. And thank you.
Okay, thank you, Vaisakh, for a wonderful talk. So I ask audience, if you have any questions, please ask Vaisakh.
I have a question.
Yes, sir, please.
The dimension witness, what is the meaning of fractional values? Like 3 root 3.
Oh, you mean in, okay.
Yeah, that's right. 2 root 3, 2 root 3, yeah.
Okay, what is the meaning as in, okay, this is the value of the dimension of witness. It does not mean that the dimension is 2 root 3. It's just that when we calculate this probability distribution and the function of the probability distribution, we'll get the value 2 root 3. It's not a dimension value.
Okay.
Okay, then I stop sharing and thank you again for the
I
organizers.
think there is no more questions. So let's thank the speaker once again. And this concludes the morning session. So I handed over the thing to sir if you have to any announcement or something.